For today's practical, you're supposed to carry out spectrophotometric determination of nutrients. Okay. So first, there are different standard operating procedures, different manuals available to determine the common nutrients in the water. So you have to realize that there are different manuals available and also different methods available depending on the sensitivity and accuracy of the method. Okay, methods suitable for freshwater river lakes may not be suitable uh, for the sea. Okay, because seawater has high salt concentration, and sometimes the high salt concentration affects the determination of nutrients. So the nutrients, most of the nutrients, common nutrients that we measure are nitrite, nitrate, ammonium, phosphate, silicate. Okay, these are the common nutrients that we measure because these are the nutrients that actually affects the primary producers. Okay, so we're talking about spectrophotometric determination. Definitely, we need a spectrophotometer. So when you have a spectrophotometer, you need to know what is the range of the wavelength that it can measure. Not all, uh, not all spectrophotometers are the same. It depends on whether they have the deuterium or the mercury lamp that allows it to extend its range beyond the visible wavelength into the UV wavelength. So the UV wavelength usually about 260 nanometers until about 850 nanometers. So if you want to measure the DNA concentration using spectrophotometer, make sure that it is able to measure the UV wavelengths. Okay. I've also mentioned previously whether uh, a single beam or a dual beam or split beam, all this will affect the stability of the machines, the stability of your measurements. Of course, dual beam or split beam, where you have a reference cell, will always be better than a single beam. Okay, and of course, single beam is a lot cheaper than a dual beam system. A dual beam system can easily be 2 times or 3 times the price of a single beam. Okay, so let's look at question number 1. Okay, prepare a standard curve. I've written here ammonium chloride from 0.1 micromolar to 10 micromolar, given that the molecular weight is 53.5. Okay, basically 53.5 grams per liter makes a 1 mole solution. Okay, 53.5 grams per liter makes a 1 mole solution. So if you want to prepare prepare 0.1, a 10. So if you want to prepare a 1 micromolar solution, that means it's a 1000 times dilution, right? So it's about 53.5 divided by 1000 times. Okay, so this is 0.0535 gram in 1 liter solution. So if you are to prepare a 0.1 micromolar, there will be a 0.00535 gram per liter. So do you foresee any problems here? Anyone? No. Yes, Afik is correct. This is very, very small. How are you going to measure this? Even if you have a micrometer where you can measure until, but I mean, all the weighing machine balances in the lab, once you reach about 3 decimal place, it's already not stable. So how do you measure it? So whenever we prepare uh, whenever we prepare standard solutions, we prefer to use dilutions. Okay, so let's just say since we are supposed to prepare a standard curve from 0.1 to 10, so 10 micromolar will be 0.535 grams per liter. So it is actually better to prepare this and to dilute it than to try to attempt preparing uh, solutions that have too small a weight. Okay, so the thing that I want to emphasize here is uh, be wary about you measuring too small a volume, too small a weight when you're preparing standard solutions. Opt instead for dilutions. So 10 micron you can go to 5 micron micromolar, 10 micromolar can go to 5 micromolar, 10 by doing a 2 times dilution. 10 micromolar can also go to a 1 micromolar by doing a 10 times dilution, and from 10 micromolar to this one by doing 100 times dilution. Okay, so basically you have to fill up your standard curve range. Okay, so do you all understand the first part of this question? Okay, so let's just say you have prepared your solutions through dilution. Okay, how do you prepare the dilutions then? Okay, so let's just say you're given a volumetric flask, measuring cylinder, and conical flask. Which one do you think you will use? Or are all the three the same? Anyone? Are all the three containers vessels the same, or do you think you should use only a specific kind to prepare the standard curve? Metric flask. Okay, it's flat bottom but with a long neck. Metric flask. Okay. Why doctor? Okay. Not all glasswares are built the same. Okay. So when you're doing standards, the volume measurement, the accuracy of your volume measurement, yes, has to be as precise as possible. Okay. Among the glasswares noted here, volumetric flask, measuring cylinder, and conical flask. The ones that is the least accurate is actually the conical flask. That's why we usually use it only for titration and don't use it for to prepare standard solutions. Okay. So if you see people using conical flask to prepare standard solutions, then definitely it's a wrong. It's a wrong practice. You shouldn't do that. Even measuring cylinders are not accurate. Okay. For standard solutions, you must always use volumetric flasks. Okay, volumetric flasks. So it's written is one question here. How will you clean your volumetric flask? Where will you dry it? Okay, do you all have a answer for this? How will you all dry your volumetric flask? I mean, you've used your volumetric flask to prepare the standard solution. After using it, you clean it up. Okay, so where do you dry it? Anyone? Okay, so once you say it's oven, then it's definitely out. Okay, because you can only air dry a volumetric flask. You cannot place it in the oven. Once you place it in the oven, the expansion changes the volume, increases the error, and it is no longer accurate. Okay, of all the glasswares in the lab, volumetric flasks cannot be dried in an oven. So if you see volumetric flasks in the oven, there's something very wrong in the lab. Okay, so please, uh, these are actually just things that when you do chemistry, you learn all these things a little bit here and there. So when you're preparing standards, only use volumetric flasks. When you're preparing standards, opt for dilution. Okay, because measuring small weights are not accurate. Okay, then use volumetric flask where possible, and when you clean it up, when you dry it, only air dry it. Okay, so even among the different glasswares, there are grade A and grade B glasswares. Okay, so here is a measuring cylinder. It's written here, grade A measuring cylinder and a grade B measuring cylinder. Okay, this is the volume of the measuring cylinder. If it's 50 mils, its accuracy is plus minus 0.5 mil. If it's 500 mil, you can get an accuracy of 2.5 mil. That's for grade A. Okay, for grade B it's 50 mils. The accuracy is plus minus 1 mil. If it's 500 mil, the accuracy is 5 mil. Okay. However, if you look at a volumetric flask, grade A volumetric flask, if it's 50 mil volumetric flask, it's plus minus 0.05 mil accuracy. Whereas if it's 500 mil, it's plus minus 0.2 mil accuracy. So from here, immediately you can see why you should use only the volumetric flask when preparing standards. Okay? And why you shouldn't be drying your volumetric flask in the oven, because expansion and contraction of the glassware itself will easily change the accuracy of the flask. Okay, so remember, even glasswares, there are different grades. Okay, and you must take into account all this when preparing standards. Okay, so this is the important points that I want to point out for this part. Any questions about this? Do you have any questions? Okay, so let's go to the next. The grade doesn't depend on the brand. Every brand will have their different grades. So every Duran, Scott, every brand will have their different grades. But for grade A glassware, usually it comes with a QC certification. So in the QC, the quality control certification, it will be written there the accuracy plus minus how many mils. Okay, so you can refer to the certificate to have confidence in the glassware that you are using. Okay. Okay. So let's go to the next one. So once you've done your, let's just say you prepared your concentration in micromolar, then you measure and you obtain a absorbance. So let's plot a standard curve. So it should be quite straightforward. So this is your so you select the data that you are interested in, then you plot a graph. Okay, you plot a graph. Okay, so it looks good. So I'll draw a trend line. Right click here to add a trend line and also to display the equation in our script. Okay, so if your standard curve is prepared properly, your R squared is usually above 0.9. Of course, if it's 0.99 and above, it's of course the best. Okay, so this shows the equation that depicts the standard curve. Okay, so you have Y will be your micromolar concentration, and this is your absorbance. Okay, so you have this equation here. So next, when you do the sample measurement, you'll get your absorbance. Okay, so how your absorbance is X, so you just have to add it into the equation, add your absorbance into the equation, to obtain the concentration of the ammonium that you are measuring. Okay, okay. Is there any problems here? Do you all see any problems with this? Anyone? Okay, first, Anis, we need to look at the formula again. This is the formula for the line. Okay, this is the equation for the linear equation for the line, the standard curve line. So Y is your concentration, X is your absorbance. So what we've done here is just we've added the absorbance into the concentration to obtain the concentration of your the concentration of ammonium in your sample. These are samples from these six samples, so we are not actually looking at averages and all that. So there is no problem with outlier. But look at the value here, and there's something wrong with this. Anyone? Anis, do you understand the concentration already, the formula? So anyone knows why there's something wrong with this set of data? Yes, Nordiana is correct. Sample 4, the absorbance, not the value, but the absorbance is too high, 1.5. If you remember the Beer-Lambert law, high absorbance is usually not accurate, and it is better to dilute your sample before running your experiment. But not only that, the standard curve that you generated, the range is only until 1.1. Okay, the the absorbance is only until 1.1. So the absorbance here is already outside your range. So it is not accurate to do that. It is better to dilute the sample before running the experiment. Okay, that will give you a more accurate concentration of ammonium. Okay, so please take note of that. Okay. So any questions? Okay. So I've told you that most of the nutrients that are of interest is the following. Okay. So we'll just go through some of the precautions and some of the things that you should take note of when when doing this kind of measurements. Okay. For ammonium, it is present in the air. Okay. Ammonium is present in the air. It is not stable. Okay. Okay. So ammonium is present in the air. Why is this important? That means there is a chance of contamination from the air itself. This is important especially for open ocean waters. Ocean waters have very low ammonium. So even breathing near the sample might actually contaminate your water sample with ammonium. Okay? That's why also when we keep samples for preservation frozen, we try to reduce the head space, which means the volume of air in the bottle. We reduce the head space so that uh, there is less contamination from the air. Ammonium also indicates whether the water has low tension, oxygen tension, whether the water is reducing. Because if you see a lot of ammonium in a high concentration of ammonium in your waters, it could indicate uh, that the waters in the system is reducing. Okay, that means the dissolved oxygen levels are low. That's why the ammonium can remain relatively stable in your sample. Okay, so that is what you can conclude about measuring when measuring ammonium in your samples. Okay, for phosphorus, it is very low in waters. Okay, so when we measure it in the coastal waters, yes, we can measure it, although it's usually about 0.1, 0.5 micromolar. However, in the oceans, it is much more lower. So usually there is we will use a method to concentrate it before measuring it. Okay, so if you're interested in measuring PO4 in the oceans, you can look out for the magic method. Okay, the magic method concentrates the phosphorus in the oceans before measuring it. Okay, so if you're measuring phosphorus in the oceans, you have to use a method that concentrates phosphorus. Okay. When you talking about silicate, the first thing you'll notice is avoid glassware. Okay, so if you look through the methods, you realize that when we want to measure silicate, we avoid using glassware. We'll use plastic bottles. We'll use micropipettes where possible. Avoid contamination from glassware because during the analysis itself, sometimes silicate can leach from the glassware and contaminate your sample. So when measuring silicate, avoid glassware. Okay. For NO2, it's straightforward. Okay. However, NO2 is usually in low concentrations. Okay. In the aquatic environment, nitrite is usually in low concentration because it is usually the intermediate between nitrate and ammonium. So usually NO2 is in very low concentrations. You usually find either a water with more NO3 or more ammonium. If you find a water with more ammonium, that indicates that the water is usually more polluted, more reducing in nature. Whereas if you see nitrate higher, that means it's usually more oxygenated. Okay, so NO3 and ammonium NH4 are usually the ones that we see in the waters. Okay, but how do you, but measuring an NO3 is actually more of a hassle, because you have to use a cadmium reduction column. Okay, you have to use a cadmium reduction column where all the NO3 is reduced to NO2. Okay, then NO2 is measured. Okay, so for NO3, we don't measure NO3 by itself. What we do is we reduce all the NO3 to NO2, and then we measure NO2. That's why if you want to measure NO3, you have to measure NO2 separately. Okay, and then the concentration from this method, we minus this NO2 to obtain NO3. Okay, so NO3 is usually not measured by itself, but measured after reduction to NO2, and then we just minus the original NO2 to obtain the NO3. Okay, so this all these nutrients are common in the seas and the water, and are useful to interpret whether the water is healthy. If it's healthy, it should have more NO3 than NH4. Okay, if it's healthy, it should have silicate, it should and a small amount of phosphorus.